Greetings, geometry students. I appreciate you finding time to get your notes taken care of. Today we're going to look at what is basically a second half to the first lesson that we did. Kind of broke it into two pieces with all the extra instructions and things like that we had to do about Cornell notes. The first video was already taking longer than I wanted, so I split it into two lessons. So now we're going to kind of clean up the loose ends from what should have been in the first lesson. Today's title is More Information About Points, Lines, and Planes. As always, anytime you need more time to write something down, press pause and then hit play when you're ready to move on. Okay, let's take a look at our objectives today. Our stated objective is the student will learn to apply Euclid's basic structures to similar geometric concepts. Now, you do need to copy down your objective. That's your first thing after your title. And the language objective, which is just my message to you of what the goal here is, the student will demonstrate mastery of the new vocabulary and connect Euclid's basic structures to those discussed today. You do not have to copy down the language objective, only the primary objective and also the essential question. And the essential question for today is, can I identify and name the new structures when I see them? Okay, so let's take a look. Okay, a new structure that doesn't exactly fit precisely into what Euclid had in mind is the idea of a ray. Now, a ray is a line that continues only in one direction. The end that does not continue is called an endpoint. Now, obviously, that's different from Euclid's first dimensional structure being the line. The line continued infinitely in both directions. A ray only continues in one direction. The other end has an endpoint. Okay. When we discuss rays, we're going to call them by their name, which is always the name of the endpoint, and then any point that is on the side of the ray that is extending on infinitely. Okay, so as always, we will call it by the type of structure that it is, and then we will name it by its name. So let's say we are looking at an example like this one. Okay, hopefully you remembered that the word ray is over in the left column of your Cornell notes. The definitions and the supporting points are over on the right side. Now we have a little diagram. Okay, that goes over on the left. And if we have to refer to this structure, this is pronounced ray AB. Of course, remember in geometry, we always name the type of structure. In this case, that's a ray. And then the name of the structure. And the only way to name this guy is ray AB. A gets the top billing because it is the end point of the ray. And if you happen to flip-flop that around and call it ray BA, you just said that the ray started at B and goes infinitely towards A, and that would be incorrect. Okay, so the end point is always listed first. Okay. If you need to refer to this in writing, we have a shortcut notation, just like we did with the line. We're going to write the end point first, and then one of the points that is on the side of the ray that extends forever. In this case, we only have one. That is the B. Okay, and we can put a little line over the top of it. However, we cannot put arrows on both ends of the symbol because our structure does not go infinitely in both directions, only goes infinitely towards the B. So notice the arrow in the little notation is going infinitely towards the B. Okay, here's another term. Terms go over on the left column of your Cornell notes. Opposite rays. We don't run into this one very often. However, it is one of the terms we're expected to know, so here it is. Opposite rays are rays that have the same end point but proceed in exactly opposite directions. Now here is an example. If you haven't figured it out by now, you will figure it out very quickly. I will always provide you with a diagram anytime a new term shows up. So for those of you that are more visually inclined as opposed to the written word, you will get a picture to go along with any new diagram always. Okay, so you can see there we have two rays that are originating at a common end point, and the end point would be B, and then we have two rays extending away from each other in opposite directions. Okay, so what we have there is we have ray BA and we have ray BC, and they are identified as opposite rays because they are going in opposite directions from each other. Now, I always try to color code my notes as often as I can, just to eliminate confusion. That way, when I talk about something like I just did in a sentence, if it's color-coded, it will hopefully match the colors back to the diagram that came before it. That way, you'll be able to identify what is related to what. So you might want to, when you do your notes, if you feel like doing the same, you might want to keep some map pencils there handy or something like that. Maybe you can color code your notes as well, and maybe that'll help you study. Totally up to you if you want to do that, though. All right. Now, if we take the other end of the line, if we do not allow it to go infinitely, now we end up with a line segment. So there's a new term over for the left side of your Cornell notes, a line segment, and the definition over for the right is a line that does not continue in either direction. And of course, if it does not continue in either direction, that means it has two endpoints. When we discuss line segments, we're going to call them by their name, obviously, just like every other thing in geometry. And the way that a line segment is named is naming off both of its endpoints. So a possible diagram that might go along with being a line segment might look something like this. When it comes time to talk about this particular structure, okay, we're going to call it, obviously, again, it is a line segment, so we will identify that, and then you list both of the endpoints. So line segment AB is an absolute possibility for the way this one would be named, and it does not matter. You can name the line segment, the endpoints in either order, so it very well could be called line segment BA. However, the tendency is to name these in alphabetical order, so you will see AB slightly more often than you'll see BA. If you need to refer to it in writing, once again, there are shortcut symbols for line segments. And as you could probably already have imagined, you put the little line over the two endpoints listed back to back, either AB or BA, only this time the little line over the top does not get any arrows because we're dealing with a line segment. Line segments do not go infinitely in either direction. Okay, now this is one that causes people trouble throughout the year, so I want you to pay close attention. Kind of the first little snag that we run into in geometry. And if you ever run across the situation where 2 points are listed back to back, now we've seen plenty of that here with talking about lines and rays and line segments. However, if there is no marking over the top of them, okay, no little line, no little ray, no little line segment, there's just nothing over it. You got two capital letters listed back to back and nothing else. This is speaking about the distance between the 2 points. Okay, so there is an example of what we're talking about. AB, 2 letters back to back, no symbolic notation in front of them or over the top of them or anything. It's just 2 letters back to back. That reads the distance from A to B. So when you see questions that are like that, your answer is going to be a number. Okay, distance is a value, some number that says how far it is from one location to another. Okay, so let's take a peek at an example. This is actually an example of what is referred to as the segment addition postulate. Not exactly necessary for you to know that it's called the segment addition postulate, and you'll see that this is very much a common sense. In fact, that is the definition of the word postulate. It is a rule that really does not need to be explained. It simply makes sense because that's just the way it's got to work. So let's look at a series of line segments that we are looking at here. Obviously, we've got a big long line segment going from T to R. Along the body of line segment TR, we have a couple of points in between Q and S. and we have some measurements provided along the way. Now, a little piece of information, something you're going to need to know throughout the year, is let's take a look at that 3 that is above the left side of the line segment. Okay, it's important to know where that 3 actually belongs and what it is actually calling. So it's saying something is 3 units long, but what is 3 units? That 3 only extends to the left and to the right until it runs into the next point. So 3 is the distance between T and Q. 4 is the distance between Q and S, and 6 is the distance in between S and R, and that's the way it will be forever on all the problems that we work with in geometry. Okay, now the question that's being asked of us now is, and let's look at that notation that just appeared on the right, it says TR equals question mark. Now it's important to know what that just asked for, because if you don't know what it's asking for, chances are you are not going to answer it correctly. Remember, when we have 2 points back to back with no marking over the top for them, this is asking for a length. The question is asking how far is it from T to R. So our answer should be a number. Okay, so let's figure out what our number should be. If we need to get from T all the way to R, then basic common sense would say, well, if you want to get from T to R, it would make sense for you to get from T to Q, and then from Q to S, and then from S to R. And that would get you all the way from T to R. Okay, so let's look and see if we know those little individual measurements. T to Q, do we know that? Yes, we do. It is marked as 3 in the picture. Q to S, do we know that? Yes, we do. It is marked as 4 in the picture. S to R, that one is marked as 6 in the picture. So if we take those values out of the equation that we have working right now and replace them with the actual measurements that came from the diagram, then what we see is that from T to R is nothing more than a simple addition problem. 3 plus 4 is 7, and 6 more than that is 13. The length from T to R equals 13. This is how you're going to answer your problems for me in geometry. Whenever you arrive at a final answer, you will put a box around it. This is announcing that this is the end of the problem as you see it, and that is where I should be looking for the answer to see if it is correct or not. That way, you and I do not have any miscommunications or problems as far as understanding what you're calling the answer or what I think you are calling the answer. So put your answer in a box. But again, this one is called the segment addition postulate. What it means is if you have a bunch of small segments, you can add them up to make a bigger segment. Or if you have a big segment, you can subtract some away from it to make a smaller segment. Pretty easy one. Okay, there you go. Short lesson for today. Next, the only things that remain are for you to write the word summary at the end of your notes and come up with your summary. 1, 2 sentences at the top, at the maximum, that summarize the information that was just covered. Also, at the end of your summary, address any questions that you may need to come in and ask for help on your during tutorial times or anything like that. And then your essential question, just reflecting back, you don't have to write it again, reflecting back, okay, think to yourself, can I identify and name the new structures when I see them? And again, you don't necessarily have to have that mastered just yet, but as we get to the end of the worksheet in class, that is the question that you should be able to answer. If you cannot say yes to the essential question, then you probably need to spend some time studying or coming in for help, things like that. All right, appreciate you getting your notes taken care of, and I will see you in class.